Hello everyone, my name is Cédric. I'm a PhD student in first years under supervision of constant Moutou. I'm working on mechanical behavior of glued laminated timber or glulam. Today I'm going to talk about some of my research work, especially on mechanical behavior of tropical glued laminated timber beams with figure joints. My outline is structured as follows. First, I will deal with context and objectives. Second, material and method. Then I will deal with experimental tests. Then I will deal with results and discussion. Finally, conclusion and perspective. To start with the context, Gabon forest has more than 400 potentially exploitable wood species, but only 17 of them are exploited. Prized for their gold property, this leads to overexploitation of some wood species, such as okum, as shown in Figure 2, where its low consumption was 61% in 2070 years. So, in the long term, some wood species could be classified at risk of extinction. One solution would be to insert the secondary wood species into composite elements made from glued reconstituted wood, such as glulam, which are composite material with various advantages. This is one of the reasons why, in recent time, their use has mainly increased in temperate countries in the construction of large structures, including. This technique will make it possible to give the value of less exploited wood species. Unfortunately, there is not enough information about the mechanical behavior of tropical glulam in literature. Tropical wood study often focus on the mechanical characterization of solid wood. In addition, the rules of the standardization of construction with tropical glulam take into account European requirements as a normative basis. Due to the lack of consistent experimental data for tropical wood species and also to African standardization. So, for this work, our objectives are: first, make a multi-criteria analysis for the choice of wood species. Then, make a mechanical characterization of the species and multi-species glulam beams. Specifically, it will be a question of understanding the mechanical behavior of tropical glulam, valuing the secondary tropical species, reduce the cost of glulam beams. Next, we have the material and method used in this work. First, we have parameter of this species and single lamella configuration. Given the wide variety of wood species in Gabon, we based ourselves on 4 criteria for the choice of species, include availability, consumption of log, mechanical strength, and finally work class. So 2 wood species with different density were correctly selected. They are Ozigo and OZ and Paduk or PDK. They were reconstituted by gluing to design glulam beams with 2 lamella or duo and 3 lamella or trio. Their physical mechanical characteristics are presented in tab 1. Before characterizing glulam, the single lamella will first be tested. Figure 4 shows the single lamella configuration. Next, we have duo beams configuration. Here, 2 configurations have been chosen for duo beam, especially when the figure joint is placed on upper lamella and when figure joint is placed on lower lamella. Figure 5 shows us there's 2 configurations. Last, we have trio beams configuration in figure 6 and calculation of mechanical parameters. So I will continue with the gluing process. The gluing took place within the Ecole Society, partner of the study. Ozigo and Paddock were combined by gluing with the phenol adhesive. Figure 7 show the gluing process. Finally, 6 configuration combined have been obtained in addition to single lamella with and without figure joint, notably 4 duo and 2 trio. Next, the experimental device. Figure 8 shows the experimental device used for a four-point bending test bench. I will deal with the experimental test. First, the lamella with and without figure joint were first tested in order to determine the mechanical properties of the spacing, but also to see the influence of figure joint on the mechanical properties. So here we have load displacement curve in figure 9 and typical failure mode observed during the test, Ozigo versus Paddock specimen. According to the load displacement curve, is noted that the stiffness and maximum load of the lamella without figure joint are higher than that of those with figure joint. On the other hand, for the majority of Paddock specimens, the first crack appear in the elastic domain, while for Ozigo specimens, they appear in the plastic domain. This reflects that Paddock and Ozigo have a quasi-fragile and ductile behavior at the fire respectively. Then we have load displacement curve and typical fire mode of duo specimen or Ozigo Paddock versus Paddock Ozigo specimen. For all specimens, stiffness has a small variation. We observe for A1 and A2 configuration a ductile behavior for Ozigo Paddock and quasi-fragile behavior for Paddock Ozigo. Last, we have low displacement curve and typical fire mode of Paddock Ozigo Paddock versus Ozigo Paddock Ozigo specimen. According to the load displacement curve, the stiffness of Paddock Ozigo Paddock is greater than Ozigo Paddock Ozigo. We also note the ductile behavior for Ozigo Paddock Ozigo and quasi-fragile behavior for Paddock Ozigo Paddock. Next, I will deal with the result and discussion. First, we have average value of ultimate bending strength of all specimens. It is observed that the value found here are lower than those of the literature and that the strength of the lamella without figure joint is better than those of lamella with figure joint. For duo specimen, Paddock Ozigo combination in A2 configuration have a better strength or 101 megapascal. For trio, Ozigo Paddock Ozigo has better strength or 62 megapascal than Paddock Ozigo Paddock or 56 megapascal. Second, we have the average value of module of elasticity of all specimens. The module of elasticity found here is close to the literature for Ozigo and Paddock specimen. In addition, the module of elasticity of lamella with and without figure joint do not differ significantly. The module of elasticity of duo and trio beams is closer than that of Ozigo solid woods. Finally, conclusion and perspective. To conclude, Paddock and Ozigo exhibit quasi-fragile and ductile fire behavior respectively. Finger joint creates a loss of strength, notably 22% for Ozigo and 42% for Paddock specimen. For duo specimen, better strength is observed when the figure joint on A1 configuration than A2 configuration. There is no significant difference in strength between the Paddock-Ozigo-Paddock and Ozigo-Paddock-Ozigo combination. The presence and position of figure drawn on the lamella do not have a significant influence on the stiffness of the beam tested. The glulam beam's behavior during fire is the same as the upper lamella for all specimens. The glulam combination tested in the study belong to strength classes GL 28, 30, and 32. In perspective, mechanical characterization at different moisture content level in order to assist to see the effect moisture content on the behavior of glulam, of topical glulam. Perform cryptex in order to assess the service life of glulam beams, and develop an analytical and numerical model of the mechanical behavior of topical glulam. Thank you for your attention.